Good morning to all. So this is Elumar from SMS College of Technology and Department of Computer Science Engineering team. So now I am going to tell about the process synchronization with the semaphore. So a semaphore is a variable or abstract data type used to control access to a common resource by multiple threads and avoid critical systems problems in a concurrent system, such as multitasking operating system. And semaphores are a type of synchronization primitive. A semaphore S is an integer variable that bought from initialization, so it's acted only through two standard atomic operations, weight and signal. Definition of weight is also as follows: so weight of s, and while s less than or equal to 0 by weight s, then definition of signal is as follows: signal of s plus plus. Semaphore usage. So operating systems often distinguish between counting and binary semaphores. The value of a counting semaphore can range over an unrestricted domain. So the value of a binary semaphore can range only between 0 and 1. So thus the binary semaphores behave similarly to mutex logs. Counting semaphore. So the counting semaphores can be used to control access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available. So each process that wishes to use a resource performs a wait operation on the semaphore. So thereby decrementing the count. So when a process releases a resources, it performs a signal operating incrementing the count. When the count for the semaphores goes to 0, all resources are being used. So after that the process that wish to use a resource will block until the count becomes greater than 0. So in the process P1, so we insert the statement like a signal of sync, and in the process P2 we are the insert the statement, so wait signal S2. So because zinc is initialized to 0, so P2 will execute S2 only after P1 has invoked and a signal of zinc, so which is after statement S1 has been executed. Semaphore implementation. To implement semaphores under this definition, so we defined a semaphore as follows: so def and the structure of int values and the structure process of list and the semaphore. So now the wait semaphore operations can be defined as a wait semaphore of s and s values. So if s values of 0, so add this process up to s list, and then the process will be blacked. And the signals of semaphore operation can be defined signal process and a semaphore of s as a value of plus plus, and if I remove process p from s to list and then wake up of a process. So the block operation suspended the process that invoke it. The wake up operations resume the execution of blocked process p. So these two operations are provided by the operating systems as a basic system call. Deadlock and starvation. So the implementation of semaphore with waiting queue may result in a situation where two or more processes are waiting indefinitely for an event. So that can be caused only by one of the waiting process. So the event in question is the execution of a signal operation. So when such a state is reduced, so these processes are said to be deadlocked. So to illustrate this, consider a system consisting of two processes, so P0 and P1. So each processing is two semaphores S and Q, so set to the value 1. So P0 and P1 of wait and wait QS and the S and Q and Q and S. Suppose that the P0 executes wait of S and then P1 executes wait of Q. So when P0 executes that Q, so it must wait until P1 executes signal of Q. So similarly, when P1 executes wait of S, it must wait until P0 executes signal S. So since the signal operations cannot be executed, P0 and P1 are deadlocked. Starvation. So another problem related to deadlocks is indefined blocking or a starvation, a situation in which process wait indefinitely. So within the semaphore, so indefinite blocking may occur if we remove process from the list associated with the semaphore in last in first out order. Priority inversion. Scheduling challenges arises when a higher priority process needs to read or modify kernel data that are currently being accessed by a lower priority process, or a chain of lower priority process. Since kernel data are typically protected with a lock, the higher priority process will have to wait for a lower priority one to finish with the resource. So the situation becomes more complicated if the lower priority process is preempted in favor of another process with a higher priority. As an example, assume we have three processes LM and H, and your priority currently being executed by the process L. Ordinarily, process H would wait for L to finish using resource R. However, now suppose that process M become runnable, they are preempting process L. So indirectly, a process with the lower priority process M has affected how long process H must wait for L to resource R. So this problem is known as a priority inversion. It occurs only if the system is more than two priorities. So one solution is to have only two priorities. So these are the priority inheritance protocols, and then that's all about things. Thank you.